Welcome back to Arts Learning. In this video, we're going to go over gravitational fields, how to draw them, what they mean, and how to calculate stuff regarding them. Okay? Alright, so if you remember this formula, which we used when I was going over the hardest questions, right? This is the acceleration due to gravity at a certain space, right? Next to, or a certain space away from a mass. So it's basically how far away from a mass you need to be to accelerate at this point. Or if you're this far away from a mass, you're going to accelerate at this rate. Because we know the Earth's acceleration due to gravity is 9.8, right? Wherever you are on the Earth, you'll accelerate at 9.8 meters per second squared. But the farther away you start to get, the acceleration starts to decrease because of this decrease. Okay? It's very similar to our formula of big G, big M, M over R squared, right? And if you remember, G, if you consider this to be G, then this just becomes M times G, which is our force of gravity. But this G is different from what we know. This G is 9.8, okay? But this G is a changing value. When you start to move out in space, you start to get different values for gravity because different objects attract at different paces. Depends on the mass of the object, depends on how huge it is. For example, black holes have huge attraction, right? Because they have a lot of gravity. Okay? And gravitational fields always point inward. So they're like electrons, but there is no outward fields here, okay? Always inward gravitational fields, always inward, point towards the mass. Think of it like the Earth is over here, right? So there's some bad continents, but whatever. You're over here. Which direction are you going to accelerate towards the Earth? You're going to accelerate this way, right? Towards the Earth. The Earth is pulling you towards itself. Gravity is the force of attraction. It's not the force of falling down, okay? It's going to pull you towards itself. So similarly, the moon is also going to have a field of gravity, right? It's also going to have its own gravity. But since it has a lesser mass, Earth's gravity pulls the moon towards it. So the moon also pulls the Earth towards it, okay? Because the moon also has its own gravitational field, right? Going like that. But the thing is, the moon is so small, we don't really feel that pull. The sun's pull is what we feel when we rotate around, when we revolve around the sun. But the Earth's pull, the moon's pull is negligent. That's why the moon rotates around us. Our gravitational field is way stronger than the moon's is. So we have effectively captured that satellite into our orbit. Okay. So there you go. That's how gravitational fields look. And I'll go into more depth. Don't think that's all. Okay. So let's try the surface gravity of Earth. So you might be wondering where we arrived at this number. G is equal to 9.8. Well, if you use the formula I just showed you, right? Big G, big M over R squared. And this makes sense where this formula is coming from, right? Because force is big G, big M, small m over R squared. So if you substitute this for G, you just get the force of gravity, which is M times the acceleration due to gravity, right? So it's not out of the pocket from anywhere. I just want to show you where that comes from. So then big G, we know 6.67 times 10 to the negative 11. And this is just experimental, okay? I can't really prove this to you. It's just experimental. People figure it out by trying stuff out. And then the mass here is just the mass of the Earth. So that also took a while to figure out. I have a short on that if you want to go check that. Over the radius of the Earth squared. Why is it the radius of the Earth? Because when you stand on the Earth, from Earth's center of mass, you're a distance of r, right? So the Earth isn't a perfectly spherical object, but imagine it is, okay? From that point of view, The radius of the Earth is where you're standing, right? You're not standing above. So this is very inaccurate to scale diagram, right? You don't have any size compared to the Earth. You're like a dot. So you're basically standing the R away from there. So it makes sense why your head would feel lower gravity than your feet, because your head is farther away from the ground than your feet. But you're still basically nothing on the scale of the universe, right? I mean, I don't mean that it's just in the sense of gravity. Okay, so you're the radius of the Earth away from the Earth, center of mass. So then it becomes 6.37 times 10 to the 6 squared, right? And once you compute that, you'll arrive at 9.8. So Newton per kg, or you could say meter per second squared. And that's where we got our little g from. Okay. So whenever we do force of gravity is equal to mg, it's really just the same thing as big G, big M over R squared. It's just because over here, right? Over here, this is for more so mg is just a convention we use because all the objects on Earth are basically the radius of the Earth away from the Earth, right? They're not going to go farther than that. That's why we just calculated conveniently and we put this to be 9.8 and we can do 9.8 times m anytime and find the force of gravity. But when you start going further out into space, that's why astronauts aren't pulled into the Earth, right? Because the rocket sends them farther and farther and farther away. So since gravity is inversely related to r squared, they similarly feel a lesser acceleration to gravity towards Earth. They still have an acceleration enough to rotate, right? That's why centripetal acceleration is the force of gravity. That's why satellites are rotating around Earth, but still, I mean, revolving around Earth, but still they don't feel enough to, be accelerated towards it, to fall out of orbit. They just feel enough to stay in orbit. Okay, so similarly, there's a null point where g is equal to 0. The null point is basically when it's very similar to the questions I was showing you regarding Coulomb's law and charges, right? Basically, if you put one charge here, if you put a charge in the middle, so given that they're both the same charges, right? Like both positive or both negative, then this charge isn't going to move because the force is going to cancel out. Same thing here. This mass wants to pull this mass towards it. So it gives it a force, okay? G2, I mean an acceleration of G2. This mass also wants to pull this mass towards it. It gives it an acceleration of G1. So then both masses are conflicted, and since they're both the same mass, big M, they don't have different masses, same distance away, so same distance away as well, they cancel at that point. Okay, so they don't get pulled. That's the null point. When there's no force of gravity acting on you. So for example, right, if you were so Earth is here, and then Mercury, Venus, Earth, Mars, right over here. So let me draw that a bit farther away. In reality, it's thousands of light, not thousands, but very far away, okay? And here, right, there's a distance away. And if you wanted a null point between Earth and Mars, if you wanted to feel no gravity between Earth and Mars, you'd have to stay closer to Mars, right? Because Earth has a larger mass than Mars, so it's going to have a stronger pull. But you can counteract that by staying a larger distance away from that mass, from Earth. So then when you stay here, you have a stronger pull here for a lesser distance. Even though your mass isn't a lot, you still have a lesser distance. Okay? So that's how it works. You would still feel force, right? Because in the universal scale, there's a sun here that's still pulling on you. And that force of gravity outweighs anything, like anything we've seen. But not anything we've seen, but anything in our solar system. So you're still going to go to that point. But between the Earth and Mars, that's where you'd feel no gravitational acceleration. Okay. So this is what gravitational fields look like for objects with for multiple objects, okay? Similar to your electrons. So I mean not electrons, just protons or two electrons, right? When you had that, they would go inwards, 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 inwards. And at some point you can't do this inwards because there's another field here, right? At some point you just sort of stretch it like that, stretch it like that. Same thing here, just stretch it like that. Okay? And it's the exact same thing, which makes sense, right? Because they both pull inward, there's not going to be enough space for both of them. So the field lines are the direction an object would accelerate if you had an object placed in that position, right? Similarly, because this object here is placed in the middle of both of them, they're the same mass, same distance, it's not going to accelerate. Okay, it's going to have g of 0. So you can assume basically that gravity acts as two electrons. That's completely wrong, I mean, in the scale, but you can assume it for how to draw gravitational fields. Think of them as two electrons. Okay? So gravity is just an electron in fields sense. And same rules apply, okay? Tighter lines is stronger field. The lines bend smoothly and never cross. The null point, they cancel. Every arrow points inward towards a mass. It's exact same stuff as charges. Just always think of negative. Think of it as negative, always negative. And because it always pulls inward towards itself, all masses should be attracted towards it. And then also same thing here. So similarly, right, because the sun is so large, it's going to exert gravitational on Earth. That's why we rotate around it, centripetal acceleration, because of that force of gravity. But we are also pulling the Earth. We're also pulling the sun with the same amount of force. It just that because the sun is so much larger, we can't do much about that. Because you know how Newton's third law, right? If you pull this one here, it'll also be pulled here. But that does start to break down when you get into planetary motion. Newton's laws are only good for things between the really, really small and the really, really big. After that, stuff starts to get complicated. Okay? So if you had a big M and you had a small m, similarly, you'd have to multiply the lines by 2. Okay? So here, 1, 2, 3, 4, 5 lines. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because this mass is, we can say it's twice as large. Okay? So that's why it would, null point would be closer to this mass, because this mass has a larger mass to pull with. The lines, as you can see, are very similar to electrons, how they act with electrons, but sometimes you might see this happen. We don't know whether it depends on your class, whether you need to draw this, but you could draw a line directly in between them, okay? But in that line, there's a null point. At some point, you have to draw the null point. But sometimes you would have to draw lines directly connecting both of them. For 3 masses, same rules, right? Same rules as what I was going over for the 3 masses for electric fields, same rules. Same charge, same number of lines. Just that there's more curves and more nuances that you need to be careful of, because you can let lines cross, but when you start getting more and more charges, it gets more and more difficult. So let's try some practice, okay? So over here, right? Practice set 4a. 2 masses. Let's actually try this one. 2 stars, m and 9m, lie 4 times 10 to the 8 meters apart. Find the distance from m to the point where g is equal to 0. And we also need to find that if the masses were equal instead, how far would that point shift? So give it a try. All right, I'm assuming you give it a try. At this point, so we need to find the null point, okay? We need to find the null point here. So the point at which big G 9m times, so just big G 9m, right? Because it's the gravitational field. G is just big G, big M over R squared. So big G and then 9m, so 9gm over R squared has to be equal to, right? It has to be equal to, actually, let me write this. First, let me write the first one. I'll show you why. So this, imagine there's an object here, right? Then the G at that point, the field, right? The field at that point is going to look like G is equal to big G, big M over R squared. And for the small mass, it's just M, right? And since we know that this total distance is 4 times 10 to the 8th, if this distance here is R squared, if we define this to be R, this accordingly has to be 4 times 10 to the 8th minus R, right? So then for the other one, it has to be big G times 9m over 4 times 10 to the 8th minus R squared. Right, and there you go. That's your equation. So you have to set these equal to each other because at the point where they cancel, it has to be equal to each other, right? So you set them equal to each other and you solve. Big G, big M immediately cancel, right? You're left with 4 times 10 to the 8th minus R whole squared is equal to 9R squared. You can take the square root of both sides. And then you'll get 4 times 10 to the 8th minus R is equal to 3R. 4R is equal to 4 times 10 to the 8th. R is equal to 10 to the 8th. So all in all, pretty simple, actually. Yeah, it's pretty simple. And that's your distance. That's the distance at which, that's the distance at which the G is equal to 0. So 4 times 10 to the 8th. So from a smaller mass, it's 10 to the 8th. From the distance from M to the point, right? So from this smaller mass, it's a distance of 10 to the 8th meters. If the masses were equal instead, how far would that point shift? So if the masses were equal, then what happens is you can represent this as basically M, right? So then M and M, so actually let me draw a new diagram to make this easier. The point where G is equal to 0 is going to be directly in between, right? They have to have the same mass, it has to have the same distance for it to be equal. So at that point, what's the middle of, let's see, the middle of 4 times 10 to the 8th? It's just 2 times 10 to the 8th, right? There you go, that's your middle. So how far would it shift? So 2 times 10 to the 8th minus 10 to the 8th. It would shift that much. 10 to the 8th times 2 minus 1, it will shift 10 to the 8th meters, okay? There you go. So, yeah, pretty neat. All in all. Now, let's try problem 4. Earth and the moon are 3.84 times 10 to the 8th meters apart. And Earth is 81 times the moon's mass. So that's a lot, right? That's why I told you the moon is kind of tiny compared to us. But we are also tiny compared to Jupiter and the sun. And Saturn, actually. Saturn as well. And we need to find the distance from Earth's center to the null point, then sketch the field and describe what a probe released there would do. Okay? So, Earth here, moon here. 3.84 times 10 to the 8 between them. So this is 81 m, and this is just like regular m. What's the distance from Earth's center to the null point? So that's just going to be, so from Earth's center to the null point, okay? So here, what we can do is we can do the same equation, big G times 80, so 81 times big G m over r squared this time. And then we can set that equal to the moon's length here, which is just big G m over 3.84 times 10 to the 8th minus r whole squared. Okay. And that should give you, accordingly, you can divide both the g's and the m's. Same steps we did last time, just the same steps, right? 81 times 3.84 times 10 to the 8th minus r whole squared is equal to r squared. Take the square root of both sides. And you'll end up with r is equal to 9 times 3.84 times 10 to the 8th minus r. Okay, so you can distribute this. R is equal to 9 times 3.84 times 10 to the 8th minus 9r. 10r is equal to 9 times 3.84 times 10 to the 8th. So r is just equal to 9 times 3.84 times 10 to the 7, right? And there you go. That's your, so maybe I can simplify this 9 times 3.84 to make it a bit smoother here. So let's see. Let's get the calculator out for that. So 9, right? 9 times 3.84. 34.56 times 10 to the 7 meters from Earth. Okay, from Earth. Then sketch the field and describe what a probe released there would do. So let's sketch the field. So let me actually get this up here. I believe, yeah, okay. So then, add a field, so over here, it's a field here, so we can just say 81 m, and then we can draw a straight line at a null point somewhere over here, very closer to the smaller mass. Okay, I'll denote it as a circle. Obviously, so I'm not going to draw 81 times more lines, okay? It's a bit excessive, but I'll just draw a few lines here. So here, technically I should probably draw 81 times more lines, but I'm not going to do that. So I'll just do what I can do here best. Right, and then right there. I mean, make sure not to cut your lines. They shouldn't intersect. But the way I'm drawing them shabbily, they kind of look like they do, but they're not going to intersect, okay? And this really gives you context under how much stronger the Earth is, right, compared to the Moon. I mean, not stronger as in strength, just stronger as in gravitation, okay? Next video, we're going to go over the triboelectric series. And yeah, just the triboelectric series, how to use it, how it works, and what are the caveats of the triboelectric series. And then after that, we'll complete Unit 6.2. We'll go over review, and we'll start 7. Okay, so stay tuned for the next video. Make sure to like and subscribe so you can continue on your physics journey and continue watching my videos. And stay tuned for the latest updates. And thank you for watching.